sac126 problem number 3. Let's get a sketch of this one. We've got a spring with a mass hanging from the end of it, where the mass is 0.550 kilograms, and the spring constant is 21.5 newtons per meter. So somebody lifts the object up and lets it go and starts oscillating back and forth. We want the time it takes for it to initially arrive at a position 0.100 meters above its equilibrium position. So they lift it up 0.2, they let it go, and they want to know when it gets to 0.1 meters above its equilibrium position. We cannot use constant acceleration equations on this one because the acceleration is not constant. The acceleration is a result of the net force on the object, and there's a spring acting on it. And the force exerted by the spring depends on the position. The more the spring is compressed, the greater the force, so the greater the acceleration in magnitude. And hence, the acceleration is changing. So we can't use the constant acceleration equations. So we want to get an equation that gives the position as a function of time and then solve for the time. If we look at the formula sheet, the one that yields that information is this guy right here. Gives position as a function of time. So what we need to do then is to find out what A is and what, let's call it 2 pi f is. Go back over here, write that down. A is equal, or x is equal to A times the cosine of 2 pi f times t. Alright, A is pretty easy to get. The person lifts it up 0.2 meters. That's going to be the maximum displacement from the equilibrium position. So by inspection, A is just the 0.200 meters. Now, the frequency, and hence 2 pi f, is going to depend on how stiff the spring is, how big the mass is. We do have a relationship that relates T for the case of a mass on a spring to those characteristics, the mass of the object and the spring constant, and we'll also use the fact that f is equal to 1 over t to get an expression for f and indeed for 2 pi f. So we've got f is equal to 1 over t, where t is 2 pi times the square root of k over m, and that's probably the wrong way. I'm going to try m over k and then take a look at it here. Square root of m over k, yep, there we go. So f being the reciprocal of that is thus 1 over 2 pi times square root of k over m, or 2 pi f is just square root of k over m. Little note on algebra here. I'm taking the reciprocal of t, where t is this reciprocal of a product, is the product of the reciprocals, so 1 over 2 pi times the reciprocal of this, and the reciprocal of the square root of a ratio is the square root of the reciprocal of that ratio. Okay, we can go ahead and get a value for 2 pi f then. We had, just going to scroll up just a little bit to be able to see our k, 21.5 newtons per meter for k, and the mass was 0.550 kilograms. So 2 pi f evaluates to 6.252 radians per second. Radian, not a true unit, a fraction of a circle. So I just put that in there. The rest of it, a Newton is a kilogram meter per second squared. Divide that by the meters. Divide the whole thing by the kilograms. And then take the square root. Kilograms cancel. The meters cancel. Square root of 1 over seconds squared is 1 over seconds. And then I just pop the radians in there, knowing that 2 pi f has units of radians per second. The only kind of unit you can do that with, a radian. Alright, so now we've got our expression for x. It's 0.2 meters times the cosine of 2 pi ft, where 2 pi f is known. So let's go ahead and solve that for t. I think I'll copy it down first. X is equal to a times the cosine of 2 pi f times t. And I want to solve that for t. Get t all by itself. First I'll divide both sides by a. Then I got to get rid of the cosine, so I'll take the arc cosine of both sides. I'm going to go 2 pi f t. I'm writing down the right-hand side over here. So the arc cosine of the cosine of 2 pi ft is just 2 pi ft. And over here, when I take the arc cosine, I just have to write it down. The arc cosine of x over a. So t is going to be the arc cosine of x over a, all divided by 2 pi f. And I've got an expression for 2 pi f. I knew that was going to be coming up a lot, so I solved for 2 pi f rather than the f itself, and that 2 pi f is all grouped together in here. T is thus the arc cosine of x. They wanted us to find it at 0.100 meters. This x is the position of the object that's bouncing up and down. It's not the amount by which the spring is stretched. So in this context, x is the position of the object relative to the equilibrium position, where I'm calling up the positive direction. And then the a was 0.200 meters. And 2 pi f we just found to be 6.252 radians per second. So what do we get when we evaluate that? T turns out to be 0.167498 seconds according to my calculator. And the values are given to 3 sig figs. So we'll round this to 3 sig figs, which is 0.167 seconds. And for intermediate results, I'm going to call T 0.1675. So as I substitute this into subsequent results within this very problem here, I'm going to use 0.1675 seconds and quote 0.167 seconds, properly rounded to 3 sig figs as the result of the final problem. But I'll get slightly more accurate results for other parts here if I use that one. For the other parts. Okay, let's take a look at Part B. In Part B, they want to know the velocity. Let's better take a read of it. Find the velocity and the acceleration at the time you found in Part A. So we'll write down an expression for the velocity as a function of time. Get that from the formula sheet as well. The velocity is a function of time given as minus Vmax times the sine of 2 pi ft, where Vmax is A times 2 pi f. Let's see if I can remember all that. Minus Vmax times the sine of 2 pi ft, where Vmax is A times 2 pi f. Let's go ahead and substitute. Our A was 0.200 meters. That's the amplitude, maximum displacement from equilibrium. And 2 pi f, I just had substituted in over there, 6.252 radians per second. So again, I recognize the radian as the one unit we deal with. It's not a true unit. And this meter radians per second I write as meters per second. And indeed we've got 1.250 meters per second to 4 sig figs. That's one more than the final answer should be quoted to. This is an intermediate result. So then, substituting the values directly into this equation, I got V is the 1.250 meters per second with a minus sign out front, times the sine of 6.252 radians per second. Let's see what that comes out to. Substitute the values into the calculator, evaluate, and I'm getting minus 1.08 meters per second to 3 sig figs. And I go ahead and interpret that minus sign for the reader. Remember I said we're calling upward the positive direction, so a negative sign in front of the velocity means that the object is going downward. So V, the vector, is 1.08 meters per second downward. That'll be part of my answer for that. Part B. Actually, I had two parts to part B, which the other one is find the acceleration. And a couple of ways of attacking that. I can use the same method that we just used. That is, I've got an expression for acceleration as a function of time. Go ahead and substitute values into that. I'm going to use what amounts to the defining equation for simple harmonic motion. This relates the acceleration to the position. And I want to find it at the same time as in part A. Well, the time in part A was that time that made it so that x was 0.100 meters. So we use the position of the object relative to its equilibrium as 0.100 meters, and of course I've got an expression for 2 pi f. I kept that all grouped together. So I'm going to use this one for the acceleration at that particular time. So at the time when the position is 0.100 meters. So if I can remember that, it was A is equal to minus 2 pi f all squared times x, which is just going to be minus 6.252 radians per second times the 0.100 meters, the position that we used when we solved that part A for the time. So it is at the time that was solved for in part A. That gives A is minus 3.90875 meters per second squared. The minus sign again means downward. So I'll go ahead and interpret that for the reader. A is 3.91 to 3 sig figs meters per second squared downward. And that does